Let's begin with something very simple. Imagine you are standing on a quiet beach at sunset. The ocean stretches in front of you all the way to the horizon. It feels endless. Your eyes can't see where it ends, but you know it does end somewhere. There are other continents, other lands, far beyond that curved line where sky meets water. Now imagine replacing the ocean with space. Replace the distant continents with stars. And instead of a wooden boat, imagine humanity trying to cross that cosmic ocean in a spacecraft. We often say the nearest star is close in astronomical terms. But that word, close, is deeply misleading. The nearest star to us besides the sun is Proxima Centauri. It sounds friendly, almost like a neighbor, but its distance is about 24 light years away. That number doesn't sound terrifying at first until you understand what a light year really means. A light year is not a measure of time, it is a measure of distance. It is how far light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 second, it can circle the Earth more than 7 times. In 1 minute, it travels farther than most humans could in a lifetime. In a year, that distance becomes nearly 5 trillion kilometers. So when we say Proxima Centauri is 24 light years away, we mean light itself. The fastest thing allowed by the laws of physics takes more than 4 years to get there. Now pause for a moment and think about that. If we built a spacecraft that could travel as fast as any rocket we have today, it would take tens of thousands of years to reach that star. Human civilization itself is only a few thousand years old. The pyramids were built about 500 years ago. A modern rocket traveling at conventional speeds would not even be halfway to Proxima Centauri by now if it had launched in ancient Egypt. So naturally we say, fine, we'll just go faster. But here is where physics steps in and quietly, firmly says no. According to Albert Einstein's theory of relativity, the speed of light is not just very fast, it is the ultimate speed limit of the universe. As any object with mass accelerates closer to the speed of light, something strange happens. Its energy requirement doesn't increase steadily, it increases dramatically. The closer you get to light speed, the more energy you need to go even slightly faster. And as you approach the speed of light, the required energy approaches infinity. Not a very large number. Not a number beyond our current technology. Infinity. That means that accelerating a spaceship with mass to the speed of light would require infinite energy. And infinite energy is not something we lack because of poor engineering. It is something nature does not allow. So the first barrier to interstellar travel is not courage. It is not intelligence. It is not funding. It is the structure of reality itself. Let's continue by looking carefully at energy, because energy is where dreams of interstellar travel collide with reality in the most unforgiving way. Suppose we decide we don't need to reach the speed of light. That seems reasonable. Let's aim for something more modest, say 10% of the speed of light. That's about 30,000 kilometers per second. Compared to light, it sounds slow, but compared to anything humanity has ever built, it is unimaginably fast. Now imagine a spacecraft with a mass of 1,000 tons. That's not absurdly large. It's roughly the mass of a small naval ship or a modest skyscraper steel frame. Big, but not science fiction big. We want to accelerate this 1,000-ton ship to 10% of light speed. The kinetic energy of an object depends on its mass and the square of its velocity. That square is the important part. If you double your speed, your kinetic energy doesn't double, it quadruples. At everyday speeds, this isn't dramatic. At relativistic speeds, it becomes catastrophic. When you plug in the numbers for 10% of light speed, the energy required is on the order of 5 to 1080 joules. That number is so large it almost loses meaning. So let's compare it to something concrete. The atomic bomb dropped on Hiroshima released about 6 to 10 joules of energy. To accelerate our modest 1,000-ton spacecraft to just 10% of light speed would require energy equivalent to hundreds of thousands of Hiroshima bombs. And that's only to speed it up. When you arrive at your destination, you must slow down. Otherwise, you simply fly past the star at enormous speed and disappear into the dark. Slowing down requires the same amount of energy again. So we double the requirement. And we haven't yet talked about inefficiencies. Real engines are not perfect. Real systems waste energy as heat. Real propulsion systems have mass of their own. The fuel itself adds weight, which requires more energy to move, which requires more fuel, which adds more weight. This feedback loop is described by the rocket equation, and it is merciless. In chemical rockets, Most of the launch mass is fuel. For interstellar speeds, the fraction becomes absurd. To carry enough fuel to accelerate and decelerate, the spacecraft might need to be mostly fuel, but that fuel itself must be accelerated. It becomes a compounding problem, like trying to lift yourself by pulling on your own shoes. Even if we turn to nuclear fusion or matter, antimatter annihilation, far more efficient energy sources, the quantities required are staggering. Antimatter releases enormous energy when it meets matter. But producing even a tiny amount of antimatter today consumes vastly more energy than it yields. Storing it safely is another unsolved challenge. Energy is not just a technical detail. It is the central obstacle. Space is not difficult because it resists motion. In fact, once you are moving in space, you keep moving. The difficulty lies in changing your motion, in accelerating to meaningful fractions of light speed. So the first wall was the speed limit set by relativity. The second wall is the sheer scale of energy required to approach that limit even slightly. These are not political problems. They are not economic problems. They are written into the equations that describe motion itself. And the equations do not negotiate. Now we come to something even stranger than energy. We come to time. In everyday life, time feels steady. 1 second follows another. Clocks tick uniformly. If two people stand next to each other, their watches agree. This consistency is so deeply embedded in our experience that we rarely question it. But when velocities become extremely high, approaching the speed of light, time itself changes. According to Einstein's theory of relativity, time is not absolute. It depends on motion. The faster you move relative to someone else, the slower your clock ticks compared to theirs. This is not philosophy. It is not metaphor. It is a measurable, experimentally confirmed fact. Imagine a simple thought experiment. There are two identical twins. One stays on Earth. The other boards a spacecraft capable of traveling at 90% of the speed of light. The traveling twin flies to a distant star and returns. When the journey is over, something shocking happens. The traveling twin has aged less than the one who stayed behind. From the traveler's perspective, time on the ship felt normal. Their heart beat at the usual rhythm. Their thoughts moved as always. But compared to Earth, their time flowed more slowly. This is called time dilation. The faster you go, the more dramatic it becomes. At 90% of light speed, time on the spacecraft slows to less than half the rate experienced by observers at rest. At 99% of light speed, the effect becomes extreme. Years for the traveler might correspond to decades on Earth. This creates a profound complication for interstellar travel. Suppose you manage to build a ship that can reach 99% of the speed of light. From the crew's perspective, a journey to a star 100 light years away might feel like only a few years. That sounds hopeful. It sounds like a solution. But from Earth's perspective, the journey still takes about 100 years to get there and 100 years to return. 2 centuries pass on Earth, while perhaps only 10 years pass for the crew. When they come home, everyone they knew is gone. Languages may have evolved. Nations may have risen and fallen. The civilization they left might not resemble the one they returned to. Interstellar travel at relativistic speeds is not just travel across distance. It is travel into the future. And there is no symmetry. You cannot come back to your original time. The slowing of time happens only for the one who moves at high speed. The universe does not rewind. Even more subtle is the fact that at these speeds, space and time mix together. Distances contract in the direction of motion. From the traveler's perspective, the distance to the star actually shrinks. This is called length contraction. It is not that the star moves closer in some mechanical sense. It is that space itself behaves differently at high velocity. So relativity offers a strange compromise. It does not allow faster than light travel, but it allows you to cross vast distances within a human lifetime, if you are willing to abandon synchronization with the rest of humanity. Time, which once seemed like a neutral backdrop to motion, becomes an active participant in the journey. It stretches, it bends, it refuses to remain universal. And this changes the meaning of exploration itself. Up to this point, we have treated space as if it were simply an empty stage on which motion happens. A vast vacuum, a perfect nothingness. But that picture is incomplete. Space is not truly empty. Even in the darkest regions between stars, there are particles, mostly hydrogen atoms, a few stray heavier elements, microscopic grains of dust, and high-energy radiation left over from ancient cosmic events. The density is incredibly low compared to Earth's atmosphere, but it is not zero. At ordinary speeds, this doesn't matter. Satellites orbit Earth at about 8 kilometers per second. Space probes leave the solar system at tens of kilometers per second. At those speeds, the few particles they encounter cause minimal damage over time. But interstellar travel requires speeds that are not tens of kilometers per second. They are tens of thousands of kilometers per second. And here, something dramatic happens. The destructive power of a collision depends on kinetic energy, and kinetic energy increases with the square of velocity. If you increase your speed by a factor of 1,000, the energy of impact increases by a factor of 1,000,000. Imagine driving a car at highway speed and hitting a raindrop. You don't even notice. Now imagine driving that same car at 100 times that speed. The raindrop begins to matter. Increase the speed again and again, and eventually even a tiny speck becomes dangerous. At 10% of the speed of light, a microscopic grain of dust carries the kinetic energy of a small explosive device when it strikes your spacecraft. At 50% of the speed of light, the energy release becomes enormous. At 90%, even a single atom hitting the hull produces radiation and particle showers that can damage materials and electronics. In other words, emptiness becomes violent. You are not flying through nothing. You are flying through a sparse but real medium, and at relativistic speeds, that medium turns hostile. So what do? We add shielding, thick layers of protective material at the front of the spacecraft. But shielding adds mass. More mass requires more energy to accelerate. More energy requires more fuel. More fuel increases mass further. The same vicious cycle returns. There is also radiation. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent astrophysical events, constantly stream through space. Earth's magnetic field and atmosphere protect us from most of them. In deep interstellar space, that protection disappears. At high velocities, radiation becomes even more intense from the perspective of the spacecraft. Due to relativistic effects, background radiation is shifted toward higher energies. Harmless microwave radiation can become more energetic in the forward direction of travel. The faster you move, the more the universe in front of you compresses into a concentrated beam of radiation. It is as if the cosmos itself brightens and hardens as you accelerate. So the challenge is not only reaching high speed, it is surviving at high speed. The irony is striking. Space appears empty and calm when we look at it from Earth. But when you try to cross it at interstellar velocities, that calm emptiness transforms into a storm of particles and radiation. And this transformation is not a technical flaw in our machines. It is a direct consequence of the laws of physics. Even if we imagine that we have solved the energy problem, and even if we design shielding strong enough to survive the particle bombardment of interstellar space, we are still left with something far more delicate than engines or metal holes. We are left with ourselves. Human beings evolved under very specific conditions. 1 gravity, 1 atmospheric pressure, a magnetic field that protects us from charged particles, a steady rhythm of day and night defined by a 24-hour rotation, a stable chemical environment shaped by billions of years of biological feedback. Our bodies are not general-purpose survival machines. They are exquisitely tuned to Earth. We already know what happens when we step slightly outside that environment. Astronauts aboard the International Space Station experience muscle atrophy and bone density loss in microgravity. Despite exercise routines, their bodies begin to weaken. Fluid shifts change the shape of their eyes. The immune system behaves differently. These effects occur after months in orbit, still within Earth's protective magnetic field. Now imagine years, decades, entire lifetimes in deep space. Cosmic radiation becomes a central concern. High-energy particles can pass through human tissue, damaging DNA. Some damage can be repaired by cellular mechanisms, but not all. Over long periods, mutation rates increase, cancer risk rises, neurological effects are possible. Shielding can reduce exposure, but perfect protection would require massive amounts of material, adding again to the mass problem. There is also the psychological dimension. Humans are social, sensory beings. We evolve with open skies, landscapes, weather, unpredictable variation. Confinement in a closed metallic structure for decades is not a trivial test of morale. Even submariners on Earth, who know they can return home, face psychological strain during long missions. Now imagine being born on a spacecraft, knowing that no planet awaits you within your lifetime, knowing that Earth is not just far away, but permanently unreachable. Would our culture adapt? Possibly. Humans are remarkably flexible. But flexibility has limits, especially when combined with biological vulnerability. Some have proposed sending frozen embryos instead of adults. If machines could maintain life, support systems, and raise the next generation upon arrival. Others imagine artificial wombs or heavily modified humans engineered for radiation resistance and low gravity adaptation. But at that point, we are no longer simply traveling to another star. We are altering what it means to be human. The deeper issue is this: interstellar travel is not merely a transportation problem, it is a biological problem. Evolution shaped us for one planet around one star. The farther we move from that context, the more we must compensate artificially. Every compensation, radiation shielding, artificial gravity, ecological life, support systems, adds complexity. Complex systems fail. And the longer the mission, the more likely failure becomes. A spacecraft traveling between stars is not just a vehicle. It is a miniature world. It must recycle air, purify water, grow food, manage waste, regulate temperature, maintain structural integrity, and preserve mental health, all without resupply, possibly for centuries. On Earth, our life support system is the entire biosphere. It is vast, redundant, self-correcting. Reproducing even a tiny fraction of that stability inside a machine is an extraordinary challenge. So even if physics allows motion between stars in principle, biology demands an even harder question. Can fragile organisms, shaped by one narrow set of planetary conditions, truly survive the immense, prolonged indifference of interstellar space? And if they cannot without drastic modification, then who exactly is making the journey? There is another idea that seems, at first glance, more reasonable. Instead of fighting relativity and trying to approach the speed of light, we could simply accept slowness. If the stars are unimaginably far apart, perhaps the solution is patience rather than speed. This is the concept of a generation ship. Imagine constructing an enormous spacecraft, not a small capsule with a handful of astronauts, but a self-contained world. Inside are ecosystems, forests, crops, water reservoirs, carefully balanced microbial systems. Thousands of people live inside. Children are born. People grow old and die. The ship moves steadily through space at a small fraction of light speed. The journey might take 200, 500, or even 1,000 years. The people who arrive at the destination star would be descendants of those who launched. The original crew would never see the destination. They would live and die knowing only that their distant descendants might step onto another world. From a purely physical standpoint, this approach avoids the need for extreme relativistic speeds. The energy requirements are still enormous, but not astronomically beyond comprehension. If you travel at 1% of the speed of light, the trip to a star 10 light years away would take about 1,000 years. Long, but not forbidden by physics. Yet new problems emerge. First, the ecological problem. A closed ecosystem must recycle everything. Air must be regenerated from carbon dioxide. Water must be purified and reused endlessly. Nutrients must circulate through soil and plants and animals without significant loss. On Earth, these cycles function because of the vast scale and diversity of the biosphere. There are millions of species interacting in complex networks. If one element fails locally, others compensate. In a spacecraft, the system is tiny and fragile by comparison. A disease affecting crops, a microbial imbalance. A slow chemical drift in soil composition, small deviations could accumulate over centuries. There is no external environment to replenish missing components. No rain from a global water cycle. No influx of minerals from geological processes. Second, the mechanical problem. Machines degrade. Materials fatigue. Electronics fail. Even with redundancy, maintaining a complex structure for centuries without access to industrial scale resources is daunting. The ship would need manufacturing capabilities on board, essentially a complete industrial civilization contained within itself. Then there is the social problem. Human societies are not static. They change with each generation. Values shift. Conflicts arise. Leadership structures evolve. Over centuries, the original mission might lose meaning. Why should a generation born halfway through the journey feel obligated to continue toward a destination they will never see? They did not choose the mission. They inherited it. Cultural drift could reshape priorities. Perhaps future generations decide to stop maintaining the propulsion system. Perhaps they redefine the ship as their permanent home and abandon the original goal entirely. Physics does not prevent a generation ship from existing. But sociology, psychology, and biology create layers of uncertainty that are just as formidable as equations. The deeper question becomes this: is it easier to move a civilization through space for centuries than it is to accept our confinement to one star? The generation ship does not violate known laws of physics, but it demands a level of stability, ecological, mechanical, and social, that humanity has never demonstrated over such timescales in isolation. And that may be its greatest challenge. When the conventional routes appear blocked, when energy demands are overwhelming, when time dilation distorts return, when radiation and biology impose their limits, the human mind does something predictable. It looks for a shortcut. Instead of moving through space, perhaps we can move space itself. Einstein's equations of general relativity describe gravity not as a force in the usual sense, but as curvature of space-time. Massive objects bend the fabric of reality. Planets curve space-time slightly. Stars curve it more. Black holes curve it dramatically. If space-time can bend, perhaps it can fold. This is where the idea of a wormhole emerges. Mathematically, general relativity allows solutions in which two distant regions of space-time are connected by a kind of tunnel. Instead of traveling across the enormous distance between stars, you would enter one mouth of the wormhole and exit somewhere else, possibly light years away. On paper, the equations do not forbid such structures, but there is a problem. In fact, there are several. First, we have no evidence that stable, traversable wormholes exist in nature. Black holes exist. We have observed them, imaged them, measured their gravitational effects. But a wormhole that remains open long enough for matter to pass through requires something extraordinary: negative energy density, often referred to as exotic matter. In everyday physics, energy is positive, mass is positive, density is positive. Negative energy does appear in certain quantum phenomena, such as the Casimir effect, but only in extremely tiny amounts under very specific laboratory conditions. Nothing remotely close to the colossal quantities required to hold open a macroscopic wormhole. Without exotic matter, the wormhole would collapse instantly. It would pinch off before anything could cross. Then there is the concept of a warp drive, often associated with the Alcubierre metric. Instead of traveling through space faster than light, the idea is to compress space in front of a spacecraft and expand it behind. The ship itself would remain inside a bubble of normal spacetime, locally never exceeding light speed. The bubble would move by carrying spacetime along with it. Again, the mathematics does not outright forbid this geometry. But again, the requirements are extreme. The original calculations demanded negative energy on a scale comparable to the mass energy of entire stars. Later refinements reduced the requirement, but it remains far beyond anything conceivable with known physics. There are also deeper concerns. Some analysis suggests that warp drives and wormholes may create instabilities, uncontrollable energy buildup, or violations of causality, allowing effects to precede causes. Nature may permit the equations but forbid their stable realization. This is a subtle but important point. Physics often allows mathematical solutions that reality does not realize. Not every solution to an equation corresponds to something the universe chooses to build. So wormholes and warp drives are not pure fantasy. They arise from serious mathematics, but they are also not engineering problems awaiting funding. They rely on forms of matter and energy we have never observed in usable quantities. The temptation is to say, we just don't know yet. And that is fair. Science evolves. But it is equally fair to say that every time we have probed deeper into nature, we have found additional constraints, not hidden loopholes designed for interstellar shortcuts. The possibility remains open in theory, yet theory, without evidence, remains speculation. And speculation is not a starship.